Any better? Like that. Excellent, thank you. And they can hear me, yes, they can hear me. Thanks very much. Yeah.
So, welcome again everybody. It's a pleasure for me to introduce you Professor Vedral from the University of Oxford. Professor Vedral is a pioneer in the field of quantum physics and quantum information, and he has received numerous awards and visiting professorship. So I don't want to take too much of his time, so I welcome you and thanks for coming here. We're looking forward for your talk that is quantum entanglement and the nature of reality.
Thank you very much. Thanks very much. I'm sorry I'm slightly delayed on the journey down from Oxford. It was heavy traffic, but I made it, and I'm very happy to have made it to tell you about the latest thinking in terms of quantum mechanics. So I'm going to emphasize the fundamental side of physics. I think that's what got me into physics myself. I know everyone is now emphasizing applications. I know you are reading probably about quantum computers, and they are around the corner, and I think they are around the corner. And I think it's no longer even an engineering question. We will have quantum computers in a few years' time. So I think that's not the issue really. I think it's a possibility, and I think fewer and fewer people are really doubting that. I think for us in physics, the exciting question really is, what does this all mean? And how universal our description of the universe really is at this stage. Do we really need quantum physics? Do we need general relativity as two different theories, gravity and quantum mechanics? Can we somehow unite them? Can we unify them at some point? And what does that mean for our universe? And I'm gonna tell you about it. And I will tell you about it in as honest way as I can do. I'll try to show you some of the contemporary experiments we're engaged with, and some of the latest thinking about this as well. And it's a very interesting picture of the universe, but you clearly have to give up the classical view, and I think this is really beyond reasonable doubt now, that it's very hard to stick to our classical concept that we see from the macroscopic world, and I hope that you will see why tonight. This is probably the quickest way I can introduce quantum physics. I always do this because I think it's possibly the best way. The title comes from Einstein's two complaints that he had about quantum mechanics. He complained a lot about quantum mechanics, even though he was one of the pioneers. He almost invented quantum mechanics himself, really. And then he kept complaining once he fully realized what this really implied, I think. Every basic quantum experiment is completely indeterministic. It really is random. There are many ways people used to say this, but I think some kind of fundamental randomness maybe is the right way to say this. So if we send a single photon at a beam splitter here. So here is a single photon coming in. Here is something that you can think of like your sunglasses now. That they're designed to let half of the radiation through, half of the light goes through, and half bounces off. Of course, there are very sophisticated ways nowadays how to make these things, but I'm not going to go into the details of that. So basically, what we mean by fundamentally random is that every time we do this experiment, and we can do this with a single photon, you press the laser, out comes a single photon. I'm just caricaturing a little bit, but it's almost like that. And then you're trying to predict which of the two detectors will click. Is the photon going to bounce off, or is it going to go through this beam splitter, as we call it? And this is something that quantum mechanics tells us cannot be predicted. So even if you have the most perfect description, you take into account all the elements of the preparation, the temperature of your laboratory, you know, exactly the range of frequencies for the laser. You have the full description of the experiment, and yet, every time you do this, you are forced to assign probabilities for these detectors to click. And there is no way that the theory can give you anything firmer than that. Einstein didn't like this because in classical mechanics, as you know, if I'm throwing a ball and I tell you exactly the initial conditions, I tell you the speed with which I throw this ball, I give you the angle, I give you the full description, then you can tell me exactly where the ball will be at any future instance in time. When it's going to hit the ground, how hard it's going to hit the ground, all of this is fully deterministic. And here, even the most basic experiment, asking the quantum system, are you going to go one way or the other, is completely indeterministic. We really cannot predict that. No one knows this. There are many ways of saying this. Some people say even the photon doesn't know which way it's going to go. Even God doesn't know that, in a way. There are no hidden variables, is how a physicist would put it. It's very interesting. Now, that's Einstein's complaint. God doesn't play dice. A friend of mine called Nicolas Gizan is making a lot of money out of this. He actually sells random number generators. And he says this is more random than anything else that a classical computer can produce. Because classical computers use a formula to give you random numbers. They are pseudo-random, they're not really random. But this guy is genuinely random. They use them in the casinos of Las Vegas. That's how good it is. And you can tell because there's a lot of money at stake. Of course, these guys want to use something as random as possible. So, unfortunately, God does play dice, contrary to what Einstein was complaining about. Now, his second complaint is, I also don't like it because it seems to allow for something he called spooky action at a distance. He thought that by doing something over here, you can affect something at a distance. And this shouldn't really be possible. All of us physicists believe that the universe is local in that sense. And what this means for Einstein and for the rest of us as well, it means that in order for me to change the slide, I can't do it from here. Something needs to travel between myself and the computer over there. It could well be me. I could be doing it. I could send a pulse maybe to do it faster, but something needs to happen between A and B for A to affect B. There's no other way. All of our physics is like this. And Einstein thought quantum mechanics contradicts that. So how would you argue about that? Imagine that instead of using one beam splitter, you put another one now. And you say, I'm not going to detect the photon here. What I'm going to do is put two mirrors, recombine these two possibilities, and I'm going to put another beam splitter here. And the question is, which way is the photon going to come out now? And the funny thing is that it now becomes completely deterministic. And this is really weird, because I spent about 3 minutes telling you how random this beam splitter is. All I'm doing now is putting another beam splitter after, and suddenly everything is deterministic. The photon never goes into detector 2, always goes into the detector 1. How can that be? It's a bit like, imagine I'm asking you to bet on a coin toss. Of course, most people would say, no way, I'm not going to bet on it, it's random, I'm going to lose my money on average. And then I tell you, oh, what about 2 coins? Would you bet now if I toss 2 coins? And you say, great, now I know exactly what's going to happen. And that's the paradox here. If you come with a classical frame of mind, this cannot happen classically. You can't concatenate 2 random processes to get something less random. And here you get kind of complete determinism. And what this forces us, and this is at the root of all our debates and everything that we discuss as far as the meaning of the universe, what this says is, which path did the photon take after the first beam splitter? it's clear that you cannot say quantum mechanically that it took a definitive path. Because as soon as you commit yourself and you say, well, maybe I don't know, but maybe it really took one or the other path. Maybe it's just classically random. Then you have a problem, because if it took either of the paths, it would come to another beam splitter, and it would have to choose randomly which way to go. So what quantum mechanics forces us, what I'm trying to say, it forces us to acknowledge that the photon really goes both ways after the first beam splitter. It takes both of these paths. There is something, and I'm saying something because I don't want to poison you with various interpretations of quantum mechanics. It says something has got to travel down both ways. You can think of maybe the photon traveling, you can think of the description of the photon traveling, you can think of some hidden potential traveling, whatever you like, something has got to travel. And what's interesting then, of course, we call this a superposition, these both things happening at the same time. And what happens then, the way we explain this mathematically, is that when these two paths meet at the second beam splitter, then they tend to cancel one another out in this direction of detector 2, and they tend to enhance one another in the direction of the detector 1. So it's very interesting, and it's interesting because I have to suddenly, my explanation switched to wave physics. I started with photons. I said, here is a particle coming out of the laser. But as soon as I come to this beam splitter, I'm telling you it behaves like a wave. It's taken both of these trajectories, it's waving, and then in one direction after the second beam splitter, these waves are out of phase. One of them is maximum, the other one is minimum, and they cancel out. Whereas in the other direction, they're both maximal. And that's the best I can do. That's quantum mechanics for you. If you take these two, God plays dice, and this kind of existence of a spooky action, you get quantum mechanics in a way. These are your axioms of quantum mechanics. This is where I teach my first year students. Well, I take a bit longer than one slide, I think. But okay, so basically, why was Einstein complaining about that? He was complaining because, and I think most of you probably have read about these beautiful experiments. There are these experiments called gravitational lensing. So I want to show you this kind of experiment, but it unfolds at the level of the universe. So you have a massive object, could be a black hole, could be a galaxy. In fact, that's how we know that black holes exist. That's one of the pieces of evidence. But if you have a massive object and there is light coming behind that object, then it gets attracted by the gravitational pull. And this massive object between us and another star, let's say, would act as a lens. It's called gravitational lensing, and it would pull all of these rays and basically focus them towards us, to be able to see this object in an amplified way. Now imagine what every photon is doing. Every photon coming out from behind this massive object can take any way. In fact, it takes all possible ways to come to us as far as quantum mechanics is concerned. So there is a photon in this beam that exists on one side of the black hole and on the other side of the black hole simultaneously. And now Einstein thought, what if I choose to detect it? And I put a detector here. I'm waiting on the left-hand side of the black hole. I think you understand my oversimplified language. There's no left and right and any of that. But I'm waiting in one part of this light. If I don't get a click in my detector, that means that I've created a photon on the other side of the interferometer. So Einstein said, this has got to be absurd. Not getting a detection here means I've created a photon at a distance. Spooky action. Can't be right. it is right. And every experiment we've done so far tells us that this is how it works. It's really bizarre, but that's quantum mechanics for you. So just remember, as soon as we don't understand something in physics, we elevate it to the level of a principle. And that's it. This is enough. I can't do it better than that. I'm hiding behind it, but that's the way it is. What can I tell you? It's really interesting. And now, how far have people gone? So basically, the person who really dramatized this, and I think this brought it to another level, because for a long time, people like Einstein and Bohr and so on were discussing the meaning of these quantum spooky actions, superpositions. What does it mean to be in two different places at the same time, or many different places at the same time? And then along came Schrödinger, who said, it's even worse than that. It's even worse, it's more bizarre. And it's bizarre because quantum mechanics has this property that when it couples to something else, it has to make this else object also quantum mechanical. Okay? Some people call this the totalitarian property of quantum mechanics. As soon as it couples a quantum object to something, it's going to make that something fuzzy as well and exist in many different states at the same time. And that was exactly Schrödinger's cat point. That's the point he was making. As soon as I couple a quantum object in many different states at the same time to a macroscopic object, it seems to me that that macroscopic object now also has to exist in many different states at the same time. And that's really weird. That's weird simply because we never observed that. When I came to this auditorium, I think most of you hopefully have seen me come through that door, not through that door and that door at the same time. I'm very well localized. I'm not in two states or many states at the same time. And the question for most of us really in quantum physics is to understand how this classical world emerges with all its kind of well-defined properties out of this quantum fuzziness. So Schrödinger said, the way he put it is he said, I'm going to give you all information about one quantum system, let's say an atom. Then I give you information about another system, another atom. And what's weird is that this doesn't constitute the joint information about these two subsystems. So it's a bit like, let's say we're having a drink in the pub and I tell you everything about my grandmother and you're getting bored already, then I take another hour, I tell you everything about my grandfather. And at the end of that you say, but can you tell me something about your grandparents? You still haven't said anything. Classically, this makes no sense. If I tell you everything about one individual and then everything about another one, that's got to include everything else that they have in common. But actually, quantum mechanically, this is not true at all. You could have all information about the joint system and no information about the individual systems. And that's called entanglement. They're entangled in such a way that each of them loses their identity, but jointly they have a perfectly well-defined quantum state. And that's weird. All along the lines of generalizing this superposition principle to more things. Here is my student wasting taxpayers' money when I send them to a nice conference in Les Houches. I think this is a snow cat. I can actually amplify. You can see a dead cat. You see a live cat. And now what Schrödinger said, you see, Schrödinger said is, if you have a photon and you really think quantum mechanics says it exists in two states at the same time, imagine that in one of these locations I put a bottle with poison and I don't do anything in the other location. So the photon goes both ways. When it goes this way, breaks the bottle with poison, and the cat that's in the same laboratory dies as a consequence of that. But if the photon goes the other way, there's nothing in its way, nothing dramatic happens, and the cat is alive. So now suddenly, because the photon could go in two different ways simultaneously, the poison could either be released or not, and at the same time, consequently, this cat ends up being alive and dead, simultaneously connected to these. And Schrödinger thought initially this was absurd. That can't be right, that even macroscopic objects have to get infected by this kind of quantum superposition. And actually, I think as time went on, he gradually changed his mind, and he probably ended up thinking that there's nothing wrong with this. It's okay, the universe could really be like that, and actually that's what I want to explore in the next 10-15 minutes. What if the whole universe is really like that? So he would push it even further. He would say there is a physicist doing this experiment, and when he enters the lab, there is a chance that he sees a dead cat, but there's also a chance that he sees an alive cat. And quantum mechanics would suggest both of these exist in the same superposition as the photon and the poison and the cat. So every time this quantum weirdness interacts with something else, it forces it to join exactly this kind of superposed state. And we haven't had a single deviation from this fact experimentally in last 120 years. It's amazing. How far can we push it is the question, of course. So this is exactly what I was describing. If you really put the cat in this interferometer and the poison, you will end up really creating these two branches which quantum mechanics, the formalism suggests, should be true simultaneously somehow. How would one test that? How would you put a dead and alive cat in that superposition? How can you do that, really? And we can't do that yet, but I'll tell you what we can do. So basically, of course, in the lab, the way we would do this is we would take a complex molecule and confine it to a very small, so this is really amplified, a manifold. These distances here are tiny. You put two mirrors so that you can confine light between them. And then you stick a molecule in one of these, stick another molecule here. These are kind of your implementations of objects in quantum mechanics that will become entangled. So what I'm saying is we can do this with complex molecules, with organic molecules, but no one has yet done anything of this kind with a living system. And I think this would be fun to do, really. It would shut up a lot of philosophers who claim that quantum mechanics collapses when it encounters life. I think to a physicist this sounds also a bit quirky. It can't quite be like that. Why should life have the special feature that we can collapse quantum superpositions? I don't think we're as powerful as that. Anyhow, this would be one of those experiments where you split the photon, either it gets absorbed by one molecule or the other, and now you entangle them. And I want to show you some experiments along those lines, actually. So here is the extrapolation of that. I'm going a little bit in the direction of Schrödinger, where you can say, okay, you described one observer. I'm calling him Bob now. Here is Bob. Here is the lab where the photon gets split in one branch. It affects the cat in a really bad way. In the other branch, the cat is still alive. It's all nice and simple. And then there is an observer that I call Bob, an experimental physicist, who is looking at this, and then unfortunately one copy of him, I don't have a better language, but that's kind of how it works in quantum mechanics, sees this dead cat, and he's very sad, as you can see. And there is another copy in that massive superposed state, which is very cheerful and says, oh, I'm so happy that the cat survived the experiment, and so on. And these exist simultaneously. And why am I saying they exist simultaneously? Because a colleague of mine, David Deutsch at Oxford, actually came up with a thought experiment. Again, it would be extremely hard to do this in practice. A thought experiment how to test that both of these options really exist at the same time. And the test would go like this. Think about another experimental physicist. Call her Alice now. There's Alice waiting for Bob to make the observation and join this huge state. And Alice here is going to do an interesting experiment herself. She's going to put a piece of paper underneath the door without looking at the lab to see the state that Bob is. Remember, if Alice sees whether Bob is sad or happy, she's automatically infected by this quantum feature. And we want to avoid that. We want her to be in charge of the experiment from outside. We want her to be that kind of, in that kind of control, if you like. So basically what Alice can do is put a piece of paper asking Bob, do you see a definitive state of this cat? And what's interesting is that quantum mechanics says to us that in both of these states, Bob would have to say yes. So she's not asking him, tell me if the cat is dead or alive. She doesn't want to know that. All she wants to know is, does the person inside the lab see one outcome definitively or the other outcome? Just to show that our observation is always definitive. There's never anything fuzzy when you look at something. And yet, when you look at something, you really do split in this way, according to quantum mechanics. It's really bizarre. So Bob would have to say, yes, I see here a definitive outcome. In this case, I also see a definitive outcome. And then the final bit of the experiment is that Alice would now have to arrange it in a way that she performs this closure of the interferometer and performs the interference. And if she can get the interference at the end, the quantum mechanical superposition, she would literally be proving that both of these possibilities existed. And yet, Bob answered that he saw a definitive state. So there's no contradiction there. This is just to tell you that even though it looks bizarre, and it looks as though we should be seeing superpositions everywhere, that's actually not really true according to quantum mechanics. Quantum mechanics says we always see a definitive outcome. It's just that there is always another copy of you that also sees another definitive outcome. It's really weird. And everything we've done so far has really been along these lines. Of course, I put Bob here because it's very hard to communicate with cats. I like cats. In fact, I don't know why Schrödinger chose a cat. I would choose a dog probably, but that's a different point here. The cat, after the experiment, would be completely fine because you would re-interfere this back to the initial state, so there shouldn't be any problem. But I'm introducing this human being here simply because I need someone I can communicate with to tell me what's going on the inside. Otherwise, any living system will do, as far as this experiment is concerned, if only we could communicate in this simple way. And so this is very interesting, that Alice can actually confirm that Bob is in this weird entangled state. There is a copy of Bob that sees a dead cat, there's a copy seeing a live cat, and at the same time, she can guide this experiment and re-interfere it to get a single outcome at the end of the whole thing. And that's really weird. That sounds almost like you can have it both ways. But in fact, that's what quantum mechanics is telling us. So this is what I'm saying here, because I'm using a slightly different language now, where people say, as soon as you observe something, you collapse the state. That's not quite true if you believe that everything in the universe is quantum mechanical. There is never any collapse. Things just make larger and larger entangled states. And that's actually the nature of reality as far as the universe is concerned, if the whole universe really is quantum mechanical. We don't know, it's a big if. So basically you say, why not introduce another observer? And that's what a physicist called Wigner did. Just to show that this chain of events is a never-ending chain. All you're doing is creating more and more superpositions in the universe. So you can say, once Alice conducts this experiment, why not introduce another observer, Mad Hatter, right? And say, why not, what kind of thing would he see when he interacted with this system? And all that would happen is that he would join these different branches which contain different possibilities in the universe. But they would all exist simultaneously if he played the game right. So it's a very interesting picture of the universe. It's called Wigner's friend, because it's a never-ending story. There could be another person now. And they too would join this hugely entangled state. And of course, the question for us physicists is it really like this? Is the whole universe really like this? We have no idea. We've tested it at various levels. This is this Wigner's friend, which I decided to illustrate. You know, there is this famous analogy, I don't know whether it was Eddington maybe, he was a phenomenal popularizer of science. I love reading this guy's books. I think still unmatched today. And I think he used this metaphor where he said, imagine there is a lunatic asylum and one of the lunatics decides to paint the garden in the asylum. And he finishes the painting, and then to his horror, he realizes that one bit is missing in the painting. Namely, he didn't put himself in that painting. And now he quickly scrambles to paint himself into the painting. And then he realizes yet again, I'm still missing from the painting. I need a painter that paints that painter. And so on and so on. It's a never-ending, they call it an infinite regression. Philosophers again don't like this. But actually, a quantum measurement is very much this kind of a story. If you take quantum mechanics seriously at that level, we don't know, but it's very much like that. It's a fascinating idea. What we do know is the following. Living systems not only do not collapse quantum mechanics, but actually they use quantum mechanics to their advantage. And that's the interesting thing. And I think you would expect that from evolution. It's a very opportunistic process, as you know. And anything evolution can use to improve the efficiency, even by 1%, will actually probably be found ultimately by random mutations and selection. After all, nature has had 4 billion years to come up with some of these things. So it's a huge amount of time. And what people reported maybe some 10 years ago is that light harvesting, photosynthesis, is actually a process that's fully enhanced quantum mechanically. And when I saw this, these were experiments from Berkeley. A guy is called Graham Fleming, he's a Brit, I think, who emigrated to the States some time ago to do his PhD. I think he stayed there at Berkeley. And now he's running a large physical chemistry group that studies all sorts of organic molecules as far as the quantum properties are concerned. And what's amazing, and I'll tell you this story just very, very briefly, what's amazing is that it seems that some of these systems that he studied, he took what we call purple bacteria that live, I think, in the Dead Sea, something like 1,000 meters below the sea level. And they get something like between 5 and 10 photons per day. So you can imagine how good they have to be at catching these photons in order to convert them into energy and to stay alive. So these are possibly the most efficient photosynthesizers that are known to us. And the way they do it is really very intriguing, and I'm going to cut a very long story short. They look like this in the caricature kind of image. They have a large antenna that you can think of as predominantly classical, which is meant to catch this photon. And then they have a very complex organic molecule here, which is meant to transport this photon energy into the reaction center, where it triggers the so-called ATP cycle, which is how basically chemists and biologists explain the energy generation in cells. both plants and animals. So what's intriguing when they did these experiments is that the efficiency with which this antenna passes the energy to the reaction center is close to 100%. At some point, I think biologists were even worried that this breaks the second law of thermodynamics. The famous second law of thermodynamics says there is nothing that's 100% efficient. There is no Carnot cycle, no thermodynamic engine that can actually work at 100% efficiency. There's got to be some loss. And it seemed to biologists that this guy is almost 100% efficient. How can that be? And it makes it even worse here, because when you zoom in, what happens to this photon is that it excites one molecule, then it has to excite another one, and so on. And the way a biologist would think about this is that this energy undergoes a random walk to get from the antenna to the reaction center. And as soon as you have a random walk, it's an extremely inefficient process, okay? These biologists were not able to explain this because biologists do not do quantum mechanics. And I have to emphasize this. I don't know how strongly to emphasize it. I always complain about this, that whenever I talk to people, they say, physics. The last century was the century of physics, but this century is the century of biology. I completely disagree with that. This also is the century of physics. And the reason for that is that this is the century where physics goes into chemistry and biology and explains things more properly. That's how I would put it. I know I might be offending some biologists and chemists in the audience, but I think this direction from micro to macro, bridging the gap, is the future. That really is what's happening now. So I think, unfortunately for biologists, I think this is also going to be the century of physics as well. I'm saying this to all the young people in the audience because that's also a question that I frequently get. You know, if I study physics, what can I do? I can do anything. It's a great training. Don't hesitate. It's a beautiful discipline. Anyhow, what we did, so this is now how you would present this probably to a scientist, if you like, and I want to show you a little bit of that, just to show you what we did. We thought, why just look at this nano bridge that communicates energy between the antenna and the center? Why not take the whole bacterium and couple it to light? Can we somehow make an entangled state between a living system and light to which it couples? So this is basically me trying to go in the direction of Schrodinger's cat, but with a bacterium. That's how far we've gone. I'm just trying to tell you about the state of the art of these experiments. And this also is a very interesting story because it happened in a pub. I was talking to a friend of mine called Dave Coles, who is in Sheffield now, and he's a brilliant experimentalist. And I was coming up with all of these crazy ideas, what I thought we could do with the bacterium to make it entangled. And every time I would suggest something, Dave would say, yeah, I think I can do that. And I kept, ramping up the craziness of these ideas. I'll tell you about some of them. And every time he would look at me and say, yeah, probably I can do that too. And I love this spirit. If you give me enough money, I can probably entangle anything you like. I think that's the spirit. This is probably true, if the universe is like this. Anyhow, if you look at the energy levels, these are just the different energies inside this bacterium. Here is the antenna that receives the photon. Then it cascades down. It loses energy as it undergoes this quantum superposed motion. So basically, to explain photosynthesis, you cannot assume a classical random walk, that energy goes one way or the other. You really have to assume that energy takes all possible ways simultaneously. It's a kind of macroscopic, if you like, entangled state at the level of this bioorganic molecule. It's really interesting. That's the best, the only way we can explain this thing at the moment. So somehow the energy gets lost and ultimately ends up in this reaction center. And what we thought is, why not take a living bacterium and put it in this very, very tiny cavity to amplify the coupling with light and see what happens. And what happens is very interesting, and that's what Dave did actually. What happens is that the levels, these energy levels, get slightly shifted, and he could actually observe this shift in each of these different experimental settings. And what that really meant is that the light which this bacterium absorbs somehow gets absorbed and not absorbed at the same time. Really like Schrodinger's cat. It gets absorbed and transferred, and in the other branch it doesn't get absorbed. And that's the only way really that we can account theoretically for these kind of plots here. And that was very interesting. So one of the interesting things for a physicist, of course, was how can we, one thing is to observe these energy levels, which basically just means you'll be measuring the frequencies of light that come out of the experiment. But how can we demonstrate that the bacterium is at the same time alive? Remember, because there are people who claim that you can't be alive and quantum mechanical at the same time, which it cannot really make any sense, probably. So what Dave came up with is the standard way of doing this in biology. There is a molecule which fluoresces, which he injected into the cavity together with bacterium. And if the bacterium is alive, this molecule is kept outside of the bacterium. It maintains its own integrity, if you like, the living system. And as soon as the bacterium dies, this fluorescing molecule would penetrate, and you could see it inside the bacterium. So that's kind of the biological witness, if you like, that it's alive. So in these experiments, you could witness both that the system is alive and that it's kind of entangled to light, which we thought was really cool. And then, like I said, why not scale it up and do this with more bacteria? I think what we really want to do is take two living systems like this and put it into this interferometer that I was describing earlier, so that you can really make one of these systems excited and the other one not excited, and at the same time the other way around. So this would be the direct analog, if you like, of Schrodinger's cat experiment. Of course, like I said, it's very hard to communicate with these bacteria and ask them, how do you feel, you know, if you're in these two states at the same time? It's probably the question makes no sense. Whereas if you could have a human being or artificial intelligence machine or something like that, you could actually maybe do that a bit better. So now I want to conclude with gravity, because I started by motivating this by saying that there are two descriptions of the universe that we have to take into account to understand and explain everything that we observe. We have quantum mechanics with all of these weird features of this kind, and we have general relativity telling us how gravity behaves. And what is interesting, and this is maybe the last thing that I kind of said I was going to be fundamental, and I'm not going to talk about technology. But one thing that's very interesting for technology is this thesis that any sufficiently complex piece of matter is a universal quantum computer. So if this property of maintaining entangled states and superpositions is really true at level of all of these, not just nuclei, atoms, and simple molecules, but also more complex molecules, then there is a certain universality in quantum mechanics that we're using exactly one and the same description independently of what the phenomena are that we are talking about. And a person like Toffoli had this fascinating idea that maybe this is telling us that every bit of nature is really a universal computer. Every little system can compute as much as the rest of the universe. So this is very interesting. And of course, what this really tells you is that ultimately, if you learn how to control different types of matter, then all of them will become quantum computers. You know, now we keep discussing which implementation will be the relevant one. But this would suggest that if you have the sufficient degree of sophistication in your experiments, anything will ultimately really behave like a universal quantum computer. It's a really fascinating idea. What about gravity? So Chiara is here, Chiara Marletto and I thought about this because we wanted to see what happens if you put together the idea of being in two states at the same time quantum mechanically, together with general relativity, which says something, I'm going to oversimplify just like I did with quantum mechanics, but general relativity says that the space around us gets affected by matter. And if I put a piece of matter somewhere, it creates an indentation in the surrounding space, which actually, in Einstein's view, is what gravity is all about. This curved space is what other pieces of matter will then respond to and move around it in the prescribed way. So he explained gravity not as a force that's mediated between different massive objects, but he kind of said every massive object affects the space, and then that space affects all the other massive objects. The problem there is that this theory doesn't understand what to do with a quantum superposition. It really doesn't. No one knows how to calculate this. So if I take a really massive object and I put it in two different places at the same time, a photon is too light, as you know, to do this. But if I take something like a biological cell and I superpose it in two different places, it's going to create one field in one place, another gravitational field in another place, and we actually don't have a clue what this means. We really don't know what this means. Completely open to experiments. If I was 20 now, I'd be jumping on this experiment. I think there are going to be lots of Nobel Prize. Of course, that's not the reason to jump on it. But I think our next big discovery in physics will come probably once we understand properly how to merge these two theories together. And there are no experiments in sight, which is why it's interesting to push this as much as you can. So what we thought is, why not, is a humorous, I think this is a newspaper coverage of this paper. I think I was trying to dumb it down as much as possible to try to explain it. I think it's a very, very simple idea, actually. So the question is really, if you make this quantum superposition, is it going to have the same totalitarian property with gravity? Is it going to force gravity to exist in two different states at the same time? And the way you can test it is to bring another quantum object, which is also in a superposition, and ask what happens when these two gravitationally affect one another. And actually a few of us, Chiara and myself, a few of our colleagues, Sugato Bose at University College in London, think that we are within maybe 5 to 10 years of being able to test this. And it's going to be interesting because a number of our colleagues claims that gravity will destroy quantum mechanics. So I think it's a very interesting one. Life doesn't collapse it. Life doesn't alter quantum mechanics, but maybe gravity does, because we genuinely don't know what gravity is all about. It's an interesting one. So I'm just going to put this final slide as a summary that basically the spirit of the research now is that quantum physics really does seem to apply to larger and larger objects that we are able to test. And this includes not just inorganic matter, larger and larger pieces of inorganic matter, but basically it includes living systems. So a colleague of mine, Marcus Arndt, is basically working on taking a virus and sending it through two slits at the same time, just as you would do a double slit experiment with a photon. And the question he's going to be asking is, which slit is the virus going to go through? And every experiment we've done so far of this kind says both slits. Everything we fired at this has gone both ways simultaneously, in a superposition. And the question is virus or a bacterium going to do the same? I mean, it's a fantastic question. What is this guy thinking as it's going through the slits? I mean, how does that work, you know? It's really fantastic. And this is really an interesting picture of the universe, because unlike how we teach quantum mechanics to our undergraduates, there are no measurements here. Nothing is definitive in this picture. All you do when you engage with the quantum system is you join an ever-increasing, more and more complex entangled state. That's just the best we can do if it really applies to the whole universe. And like I said, not only are living systems quantum, but they seem to be using it deliberately. This is extremely hard to prove in biology, of course, that something evolved to utilize that. But I think many of my colleagues in chemistry and biology believe that it must be that the living systems are doing some simple quantum computation themselves. And then finally, what I said is that gravity could really be the last frontier, and we really don't know what's going to happen when quantum mechanics encounters gravity. Again, some people would bet that gravity will make quantum physics classical. I think it's unlikely. I think it's unlikely we're ever going to go back to the classical world. It really isn't classical. I think what's going to happen is that something even weirder will come up, and then we're going to be arguing even more about the nature of reality. We're probably going to nostalgically be reminiscing about the good old days of entanglement, when it was all clear to us what entanglement meant, and somehow there is something even weirder now. But I don't know what that is, and I would love to know that. Most of us in quantum physics are actually frustrated with how successful the theory is. We want it to fail. Please fail so we can make our mark. That's how physicists come up with new descriptions. That's actually how, you know, our claim to fame, if you like, when this happens. But it hasn't happened for a long time, and we really don't know how far we can push it. And I think that's really the most exciting question for us in physics. Thank you.
Thank you for the wonderful talk. I'm conscious that some of you need to catch a train or a bus, and so feel free to leave at this time before we go ahead with the questions.
Yes, I'm sorry.
Thank you.
I still have time for questions. Of course, if you feel uncomfortable.
Yeah, thank
Okay, so if you have any question, raise your hands. There will be Danny and Jill that can come towards you, and we go ahead.
At the start of the lecture, you talked about tossing coins.
Yes.
With one coin, it could be head or tail, dead or alive, or one or both. If you've got two coins and you toss them, and you say one's going to be head, one's going to be tail, I don't say which one's which.
Yes, with two coins, actually, classically speaking, this uncertainty can only become worse, because now you have 4 outcomes to bet on.
Yeah.
So you're going to have to ask what happens after the first beam splitter, predict that, and then ask what happens after the next beam splitter. But quantum mechanically, that's exactly what you're not doing, actually. That's what's interesting about this.
Two coins, two
The 2 coins are 2 options.
They're identical.
They're identical.
With 2 coins.
2 options in the sense that you are betting at 2 different instances of time. That's right. So the beam splitters, ideally speaking, must also be identical. So there mustn't be a way of this. So whatever the first beam splitter does, ideally you really want to design the next one to do exactly the same. So that would be the quantum analog of that. The difference is that you are not betting first on the first beam splitter, because if you did that, you would have to make a measurement, and then you would get one of the outcomes, and that would affect what happens at the next beam splitter. That's one way of putting it. So quantum mechanically, you're going to have to wait for the first beam splitter to converge these 2 possibilities back at the second one, and only then do you make this detection. So you are right. If you did the same quantum mechanically as classically, and you really forced a bet at 2 instances, you would get the same result as classically.
So when you toss the coins, you do them sequentially.
That's it. That's it, yes.
Presumably, if you are tossing the 2 coins simultaneously,
Yes.
I expect that they will have the same face. I get 2 heads and 2 tails.
And this is what I was trying to say would be the analogy. That if you were tossing 1 coin and you really repeated this many times, and you did the statistics on the sequence, you somehow realize it's really right, it's 50-50, it's random. But then suddenly, as you're tossing 2 coins simultaneously, they always come out heads, let's say, which would somehow be the quantum analog. And then the question is, how can that be? And I think with coins, of course, it's hard to, you couldn't do that, because you would have to somehow say that both of these options exist at the same time in a superposition. And again, a person like me would say it's a question of money. Probably even that could be done, but it's an extremely hard experiment. So I'm kind of talking about the classical world in this, yes.
Hello. I think number 3 is the one that fascinates me. Living systems
Yes.
could be in fact utilising
Yes.
quantum effects to improve their performance. We recognise that certain chemicals are in living beings, but why is it a living being?
Yes, it's an excellent question, and I fully empathize with your sentiments that this is a fascinating question. This is really an amazing question. When I go to these conferences, you get a range of views. Some of them saying this can't be right, it's impossible, it's too costly for a natural system to do that. Others would say no, it's perfectly possible that that's done, and in fact it would be surprising. Some people would even go as far to say that if this was true, then quantum computers would really be the only technology that we discovered that wasn't discovered by natural selection. Everything else, somehow nature came up with prior to us and independently from us. So it would kind of be weird that quantum computers are really suddenly something that we came up with and natural selection didn't. I think what's interesting there, exactly as you pointed out as well, could you push this even further? Could you argue that life could not exist without the world really being quantum mechanical? Maybe life is not compatible with classical physics either, and even at the beginning of evolution you required quantum mechanics. I think that's definitely a fascinating question. And the other one is to do with our emotions, thought processes as well. Are there any quantum effects there? My colleague Roger Penrose would certainly argue that even consciousness is somehow connected with quantum mechanics. And I think this is what we aim to test in the future. They are fascinating questions. Yes?
I've been wondering recently whether telepathic communication say between identical twins or a mother and their offspring, there may be some system in each of their brains which, if one has a thought, then it affects the one in the other person.
Yes, I think this is also an interesting idea. Maybe I have two comments about it. One is that this kind of communication doesn't seem to, if this exists, then it doesn't seem to require quantum mechanics, in the sense that even a classical field of light may be able to explain some of these communications that are going on. So I wouldn't jump to quantum mechanics immediately if you really believe that some kind of communication exists. And the other statement is that we really lack experiments in any of these directions. As far as so my colleague Arthur Eckert told me that recently that there was a neuroscientist in Singapore who is kind of developing experiments along those lines. So, you know, rather than just testing simple quantum objects and whether they're entangled or not, can you really amplify this to the human level and claim that there is some kind of spookiness at that level? I think these are all good questions. It's just a question of how to target them experimentally, conclusively, because you're talking about extremely complex systems. And it seems to me there is a big gap to bridge before we somehow get to that level. Yeah.
You said that if quantum physics could understand its influence in gravity, some people said that we could go back to the classical physics, and I want to understand how that would happen.
I don't know, actually, that's a good point. And in fact, they don't know, is even more important. No one, so I think what's interesting here is that you are really trying to anticipate the new fundamental equation of physics. And at two extremes are the two possibilities where you force gravity to really behave fully quantum mechanically, which would entail exactly what I said. Even gravity would exist in many different states at the same time. So you wouldn't have just one space curved, but you would simultaneously have many different curvatures, it coexisting in the quantum mechanical way. So it's clear what that means. The other extreme is much less clear. And I think what people do is come up with some kind of equation that's going to force this quantum mechanical superposition to really collapse and localize in one state or the other. That's what people have in mind. But how this happens, no one knows, of course, because they're jumping outside of the existing theories of physics, and they have to really anticipate some kind of new equation that would gradually, maybe with the size of the object, destroy quantum superposition. So we actually don't have an answer. There are many competing theories in that direction.
From what I understood from your lecture, we can already entangle two particles.
Yes.
Is that correct? And interacting with one of those particles would imply that the state of the other particle is changed, correct?
Not quite. That's actually where you have to be very, and in fact that was exactly Einstein's complaint, that something like this may happen. So the way we would phrase it now is that actually if you act on one of these particles, it looks like you can do something to the other one. But in fact no experiment can tell the difference at all. So really, even to change the state of a distant particle, even if it's entangled with you, you still have to walk over there to that particle and make that change. So it's quite interesting that within quantum mechanics, we also don't allow any of these superluminous, faster than the speed of light, instantaneous communications. So it's a perfectly local theory in that sense. It's very interesting. But some people would say, if you believe that certain properties exist, then, by making a measurement on one half, you could do something to the other half. But it kind of entails an extra degree of belief that's, I think, unwarranted as far as we are concerned. Yeah.
One last question.
I have something like a philosophical question on the meaning of existence, that you say the particle exists in two states at the same time, but at the end of the day you can only measure probabilities outside the experiment or whatever. So you cannot actually measure in the middle to see what's happening. So what do you understand what you
It's a good point. It's a beautiful question, actually. We have to think exactly in this way, how to justify that statement. So I think, just to repeat the question, I claim that things exist in many different states at the same time. But if I were really to make a measurement, then suddenly I would randomly get only one of these states. I wouldn't get all of them, at least as far as one observer is concerned. And the question is, how would I convince someone who's skeptical that things still really exist in many different states at the same time? And the trick is not to measure it. Actually, this goes to the heart of quantum computation. And the idea goes back to David Deutsch again. The idea is that you could perform a different transformation. So, for instance, with a photon, you could put one type of a glass in one path and a slightly different glass, say a bit longer, in a different path. So you don't want to detect whether the photon is here or here, but you want to affect it differently here to here. And in David's mind, this meant I'm going to compute one computation here, and I'm going to do a different computation here, and then I'm going to put them together. And that's the key bit. So we do know that we can affect things differently, and then when we put them together, we know that we did it simultaneously, because otherwise we cannot explain how they combine back to interfere. But the key is not to detect it. If you do get a click, you've joined the superposition yourself, basically, if you like. You entangled yourself to the system. And that's effectively like a collapse in this language. The trick is to really do different things in these branches without collapsing, and then interfere it back. And this is really amazing. And if you scale this up, you will get your universal quantum computers, basically.
Okay, I guess we need we have a lot of questions, and we can finish now. And thanks again, Vlatko, very wonderful talk. And before we finish, I just want to announce the next talk. That will be on Wednesday, 6th of November, and they will be Endlessness and the Future of Electronics. So, looking forward to have all of you here. And it's at 7 p.m. So, 7 p.m. it starts here. And you can register on Eventbrite. Okay, good to see you, and have a good night. Thank you.